So in section 13.5 we're looking at areas under curve, and before we get into areas under curves, let me just remind you of something. If I've got y equals a function of x, okay, well I'm going to change that into z equals a function of x because I'm going to want to use my y later on. So I'm just going to introduce a z, but just think of it as a y, right? So y equals a function of x and y equals x squared, right? Then dz by dx would equal 2x. And if you think back to the differentiation chapter, the way that we got that was that we looked at a change in z divided by a change in x. So delta z divided by delta x. That was, we got that from our limit definition of an integral. So it's a limit as delta x tends to 0 of f of x plus delta x minus f of x divided by delta x. Limit as delta x tends to 0 of that lot, okay? Now, it's a while since I did the videos on that chapter. I can't remember. I think we may have used an h instead of a delta x there. But if you've not met this before, this delta x, a delta like that or like that as a capital lowercase delta or a capital delta is just a symbol that's often used for a change in something. So a delta x is a change in x. And just as I'm speaking, trying to flip back to the differentiation chapter because I will have stuck to the same notation as the book, and I've got a feeling that in that, yes, we used an h there, okay? So that's our limit definition of an integral, but instead of an h, we're using a delta x. And if you remember, in that, the little h that we had was a small change in x. So we often see it written with a delta x, okay? Well, f of x plus delta x is z of, so z is our function of x. We've got z in terms of x, so f of x, this you can think of z plus a little bit, and this is z on its own, right? So let me try and make that a little bit clear. Here's our x, here is our x plus delta x. So if this is x, that's the input, then the output we call z. If I do x plus delta x, then this here is going to be z plus z of x plus delta x, right? If I input the x plus delta x, this is the output that I get. In other words, if we make a small change in x there, look, we've got a small change in z there. And it might be a positive change, it might be a negative change, depending on whether this function is increasing or decreasing. But the derivative is this vertical change divided by this horizontal change, like a gradient is change in y divided by change in x. So the shorthand for that limit is delta z divided by delta x, or really the limit as as delta x tends to 0 of delta z divided by delta x, right? That's how we think of a derivative. Now I'm trying to get the big picture here, right? This is what a derivative is. If you make this distance smaller and you do that y change divided by x change, the limit of that is the derivative, okay? Now, what I'm going to show you now about integration, we're skating over a lot of the details, and if you are going to do this in a thoroughly formal mathematical way, it takes a long time and there's a lot of extra notation. We have to think very carefully about what we mean by limits and how limits work and learn all sorts of things. But broadly speaking, a derivative is if you do y change divided by x change and you take the limit as those distances, that vertical distance and that horizontal distance both get smaller and smaller, okay? So let's bear that in mind. And now let's introduce something which will temporarily seem absolutely irrelevant to what I've just said, something completely different. And that is this. If I've got and I'll stick to the same notation as the book here, so I've got any old function, which we're calling f of x, and then I've got an area up to a particular x value here. So I'm going to pick an x value, and I'm going to say, well, imagine the area to the left of that. And that we're going to call area. And I'm calling it a brackets x because this is a function of x, okay? If I move the x, the area changes. So the area under the curve to the left of the x going off down to minus infinity, all right? And we're interested in this area. That's what we're interested in. Now, let's just have another look aside. Why would we be interested in that area going off down to infinity? That's an odd thing to be interested in? Well, first of all, we're not interested in just finding the area down to infinity. We're interested in finding that area as a function of x. So if I give you a value of x, you can tell me how big that area is, okay? Secondly, that might be more sort of practically useful if you think of it like this. Let's call this A here and this B here. Well, if I take A of B, that's that area there, okay? And if I take, excuse me, so A of B is the area I was just putting in black, isn't it? So A of B. A of little a is that area in red. So if I wanted this area on the curve between A and B, then I could do A of B take away A of A, right? So I could find an area on a curve. I can find any area underneath the curve that I want to, and that perhaps seems like a more practically useful thing. And that is indeed where we're heading, right? So this is areas under curves between two x values. So you can draw a curve, you can draw two vertical lines, and you can say, right, I want that area in the middle. The way that we're going to find that is we're going to do it exactly and algebraically, and we're going to think about this capital A function first of all, okay? So if I give you an x input, let's say x is 7, if you knew this function here, you'd be able to say, okay, well, I'll do the following calculations with 7. I'll substitute 7 into the expression for A, and that will tell me this area. And then if I wanted to find an area between 2 points, I could do it with that little method there. So let's consider this function A, and let's think about what happens if I add a little bit to x. Okay, so if I've got x there, and I've got x plus delta x here, so I've changed x and I've added a little bit there, okay? Well, what I've done to A is I've got an extra little bit of area there as well, which I'm going to call delta A, all right? Now, the height of this bit here, let's change colours again, the height of this bit here is what I get when I put x into this function y. So if I do y times by delta x, then I'm doing that red line times by this little horizontal here, and I'm going to get an area which is very close to delta x, to delta A, aren't I? All right? Now it's not going to be exactly equal to delta A because this isn't a flat top, so that area would look like this, and I'd be missing out on this little tiny triangle at the top here. But it's going to be pretty close, okay? Now if I just take that, I can think of that as delta A divided by delta x equals y, okay? So y, function y, is equal to delta A divided by delta x. Now, let's think about this for a minute. Delta A divided by delta x is, sorry, and this is still approximately equal at the moment, okay? It's not exactly equal. They're almost the same things. Now, how can I make this approximation more accurate? Well, I can make it more accurate if I made delta x smaller, because I'd have a thinner strip there. I would have a smaller delta A, and have a smaller distance, but also that little triangle at the top, or it's not quite a triangle, it's got a curved top, but that little space at the top, which is not included, would be smaller. So I get more accurate when I make delta x smaller, and that makes delta A smaller. So what I'm saying is if I take the limit as delta x tends to 0 of the change in A divided by the change in x, then that is going to be equal to y. Okay, so my function y is going to be equal to this, and we've just said that that is the definition of the derivative, right? So y is equal to the derivative of A with respect to x. Now, take one more step. What's the opposite of differentiation? It's this new thing that we've called integration, right? So if I integrate y with respect to x, if I integrate the derivative of A with respect to x, and if I integrate that with respect to x, well, on this side, look, I've taken a function, I've differentiated it, and then I'm integrating it. So that's going to give me the function back. So if I integrate y with respect to x, that is this function a, okay? Now, might be a bit fiddly, you might want to stop and go back and rewatch that video, but what we're, the important stage, the important sort of summary of all this is, here is my function, here is an x value here. If I want to find the area to the left of that x value, all the way down to minus infinity, that is called a of x, it's a function of x. If I take the function and I integrate it, then the integral is going to tell me the area, okay? That's the summary of it. If you remember this bit from up here, if I've got a function that looks like this, and I've got values a and b there, if I take a of b and I take away a of a, so if I take that, what we did before is the black area, take away the red area, remember that from this diagram over here, then I'm going to get the area between a and b, okay? Now that is what we've learnt in section, this is where it was sensible in section 13.4 to introduce us to what a definite integral was first, because now we should be thinking, oh, hang on, well, what that is there is the integral of y with respect to x evaluated at a, in the integral of y with respect to x evaluated at b, take away the integral of y with respect to x evaluated at a. In other words, that is the integral from a to b, that's that definite integral, isn't it? So that definite integral will give us the area under the curve between a and b. Okay? Now all of that is a sort of quick version of roughly what the truth is. If you're going to do the proper mathematical proofs and check that all that works, then we need to work a lot harder. And you might have spotted that there's certain bits where I'm slightly hazing over the details. And if you haven't spotted, great. If you have spotted, I'm deliberately not worrying about the details for two reasons. Firstly, we don't need to know them for this exam. And secondly, the details are so complicated that we'll lose sight of the bigger picture. What we're trying to do here is get a summary of the plot, if you see what I mean. If at some point you're interested in going and reading every detail of exactly how all that works, then great, but you need to get used to integration first and then realise kind of what it is you're proving, and there's a whole area of maths devoted to checking these sorts of things. So I'm not going to go any further into it for the moment. Let's try an example, because although all of that is complicated, that's where the information comes from. Actually using it shouldn't be too bad. So, in the first example, in example 9, we get y equals 20 minus x squared. I can rewrite that as 4 minus x, 5 plus x, and that means that I can sketch the graph and it would look like this. It would cross at minus 5 and at 4, okay? Now if I'm interested in this area here, well, the x value here is minus 5, the x value here is 4. If I want the area under the curve between one x value and another x value, I integrate from minus 5 to 4, so from the lower x value to the higher x value, I integrate that function with respect to x. That definite integral will give me that area. Okay, that is this whole section in a nutshell. That definite integral will give me that area. So here we go, integral from minus 5 to 4 of 20 minus x squared with respect to x. That is 20 integrates to 20x, x integrates to minus x integrates to minus a half x, x squared integrates to x to the power of 3 divided by 3 into a square set of brackets. I'm not going to worry about adding the constant because this is a definite integral, so we don't have to worry about it. I take the 4 and substitute it in, I take the 5 and substitute it in, and at this point, it's on page 298. I don't think I'm helping anybody by doing all the arithmetic for you, but that's, substitute that in and you've got the answer. The answer turns out to be 243 divided by 2. That is the area under that curve there, okay? It's that simple. I suspect that by this point a lot of people are ready to move on, but just in case, I'll pick an example from exercise 13, because I've just given you a lot of complicated details, I'll do question 3, or a quick bit of question 3. I've given you a lot of complicated details. Let's do one more so you can see the pattern of kind of how straightforward the questions are compared to the derivation. If you don't think these questions are straightforward, practice the differentiation chapter, practice the first half of the integration chapter. If you're happy up to section 13.4, then doing this is only an extra stage. The only extra stage is this. Here I've got a function which they tell me is y equals 3x plus 6 over x squared minus 5, and it looks like some horrible hideous function, and if you look at the sketch of it in the book, it's not a nice neat shape that we're familiar with, but that doesn't matter. I want to know, I'm told that equation, I want to know this area, I'm told that this x coordinate is 1, this x coordinate is 3, and I want to find this area here. So I look at that, and the only new bit of information in in section 13.5 is that area there is the integral from 1 to 3 of the function of y, the function of x, sorry, with respect to x. So that definite integral gives me that area. Once I know that, well, we learned how to do this in section 13.4, so we should be able to integrate that, substitute the limits in, and so on, okay? So that is the only new stage. If anything else is bothering you, if you can do that, but you then get stuck, go back and practice 13.1, 2, 3, and 4, and you should be there. Okay, that's that for this section.